Hey guys, it's Miss Johnson and I'm here to bring you our notes for Unit 6 Learning Target 5. Today we are talking about exponential equations that are specifically exponential growth. These are equations that are increasing, so it's a specific type of exponential equation. So exponential growth equations have a standard form that looks like this. Y equals C times the quantity 1 plus R raised to the t amount. So C is whatever our starting amount is, our initial amount. R is going to be the rate of change. We want to express that rate of change as a decimal. Often it's given to us as a percent, so we need to switch that into a decimal. T is our time. Now you're probably wondering, what's the 1? Well, this is exponential growth. So if we say something has grown 30%, we have to start with 100% as our base and then add the 30% to it. So that's where that 1 comes from, because 100% as a decimal is 1. So we're starting with 100% of something and then we're increasing from there, which is why we add whatever the growth rate is. And then just like in other exponential equations, that first value, the C out front here, our C value is also the y-intercept. And that was the same thing when we looked at our standard equation of y equals a times b to the x. A was our y-intercept out front, okay? All right, so now let's just practice taking all these percents and turning them back into a decimal, because this is probably something we haven't done in a while. When we think about a percent, percents are out of 100, okay, right? So 100% is our total. 100 has 2 factors of 10, okay? So 2 factors of 10, meaning 10 times 10 gives us 100, right? Okay, so 2 factors of 10. Each time you move the decimal point, that's 1 factor of 10. When I slide my decimal point in either direction, I'm using 1 factor of 10. So if I want to use 2 factors of 10, I need to move the decimal 2 places. Okay, so if I'm moving the decimal 2 places, that gives me my factor of 100, okay? Now in this case, we are dividing by 100. This 12.4% is 12.4 divided by 100. When you're dividing by 100, that means you're going to move to the left. You're going to make your number smaller, okay? You want to make your number smaller. You have to move your decimal point to the left, because that's what division does. If we're dividing by something that's bigger than 1, our number gets smaller. So we're going to take our decimal point and we're going to move it 2 places to the left. And that's regardless of what type of number we're starting with. Even if I'm starting with something like over here, 0.7, I want to move it 2 places to the left. So this one, I'm going to move it back and then back again, and I get 0.124. That's my decimal version. Okay, my decimal form of the percent. 6%, the decimal is if you don't see the decimal point, then it's at the end of your number. So 6%, if I have my decimal point at the end of the number, I move it back 2 places, and I get 0.06. This 0.7%, again, I see a percent sign, I still need to move it 2 places to the left, even though it's in front of the 7. That doesn't matter. The fact that I see a percent sign means I go back 2 places. So this decimal form is going to be 0.007, okay? So regardless of where your decimal point starts, you always want to move it back to the left. Okay, so now let's take a look at these equations. It says write and graph an equation in an exponential growth equation based on the given information. I've got a starting value of 8 and I've got an R of 0.45. So remember that your standard form of the equation is y equals c times 1 plus r raised to the t power. So in this case, we're going to have y equals, my c is 8, and then 1 plus my growth rate of 0.45 raised to the t power. Now, t is the same thing as x in these equations. It's our independent variable. The reason we use t is because in exponential growth, we're always talking about time, but it's still your independent variable. So this is also the same thing as your t, okay? okay? Now, the way we graph these is the same as how we graphed our equations back in lesson 2. Or lesson 3 maybe. We do -2, -1, 0, 1, 2, 3. And then go ahead and plug those into your calculator. So I'm gonna take that -2 power and I'm gonna plug it into my calculator. I type in 8 times, I'm gonna open a parenthesis and do 1 plus 0.45, close my parenthesis, raise it to the -2 power. Right there, I get 3.8. Do it again, 8 times, open parenthesis, 1 plus 0.45, raised to the -1 power. I get 5.52. Do it again, 8 times, I think you can probably figure out what's gonna happen here. Raised to the 0 power, and this one's gonna be 8. Okay, that's that y-intercept that we always talk about when x is 0 and the y-intercept is the same as the starting value. Okay, now do it with 1. 8 times 1 plus 0.45 raised to the first power, I get 11.6. 8 times 1 plus 0.45 raised to the second power, I get 16.82. And then 8 times 1 plus 0.45 raised to the third power, I get 24.39, roughly. All right, now let's go ahead and put those on a graph. So at -2, I'm at 3.8. I mean, it's right about there. -1, I'm at 5.52. 0, I'm at 8. 1, I'm at 11.6. 2, I'm at 16.82. Almost 17. And then 3, I'm up at 24, which is going to be like way up here somewhere. So we don't see a whole lot of the curve happening in this one, but I can imagine that it's going to curve down and go to the left. This is one that's going to approach 0. I'm not adding or subtracting anything at the end of this equation, so it's going to approach 0 at some point. We didn't see a whole lot of that because our lowest value that we have there is the 3.8, so we don't really know where it's going to curve to the left, but that's okay. That's the graph that we have. All right, let's try it again. I have a C of 6 and an R of 13.4%. So the first thing I recognize is that I have a percent sign here. Because I have a percent sign, I need to take this guy and move it back 2 places. So my growth rate is actually 0.134. Now, I didn't do that in the previous question because the 0.45 didn't have a percent sign after it. If it doesn't have a percent sign, don't move your decimal. This one had a percent sign, so I do have to move my decimal. That's going to make my equation y equals 6 times 1 plus 0.134, and again raised to the t power. Okay, so I've got my equation. Now I'm going to go ahead and make my table of values. And again, I'm going to graph these the same way that I did when I was graphing back in lesson 3. I make the same x values each time, and then I fill in the y values after plugging them into my calculator. So I've got 6 times, open a parenthesis, 1 plus 0.134, close a parenthesis, raised to the -2 power, I get 4.67 there. Then 6 times, open parentheses, 1 plus 0.134, close parentheses, negative first power, 5.29. I know what's going to happen here, but again, if you don't remember this, that anything raised to the 0 power is 1, it's okay, just type it in your calculator and your calculator will tell you. What happens with 0 is all of this stuff falls to 1. This all falls to 1, and then you have 6 times 1, which gives you the 6. All right, let's do it with 1. 6 times, open parenthesis, 1 plus 0.134, raised to the first power, 6.80. And then 6 times, 1 plus 0.134, raised to the second power, 7.72 roughly. And then 6 times, 1 plus 0.134, raised to the third power, 8.75. Okay, I want you to take a look at your y values here, okay? The growth in your y values is very gradual in this question. I go from about 4.5 up to just under 9. That's not a whole lot of growth given our x values are increasing, okay? that is connected to the fact that our growth rate is not very much. Our growth rate is pretty small. It's only going up by 13% each time. That's not a ton of growth. That's not a really high value. So that's why our Y values don't increase a whole lot here. We don't see that dramatic increase where it jumps way off the graph. We just don't have that in this question because our growth rate is pretty low. So that's one thing to kind of take note of as you're making these exponential equations. All right, so let's put it on the graph. Negative 2, 4.67 is right about there. Negative 1, 5.29. Again, it's not a whole lot of growth, just barely above the previous one. 0 is 6. Then I'm at 6.8. Then I'm at 7.72. And then I'm at 8.75. So it almost looks linear here. It's not. If I were going to increase this, let's say I'm just going to type in 10 just for grins and see what I get. 6 times 1 plus 0.134 raised to the 10th power. I'm just picking any other value. When I did 10, I got 21.1. So my 10 is way up here. So that just helps me kind of connect my curve. I know that it's going to go there and it's going to increase. And again, this is going to go down, but it's going to go down really gradual. It might not even approach 0 for a really long time out in the negative world if I were to increase my graph there. So really gradual increase, and that just comes directly from the fact that our growth rate is pretty low. Let's take a look at number 6. Now we're going to do some application questions. It says in 1971, there were 294,105 females in high school sports. Since then, the number has increased at an average of 8.5% per year. It says write an equation to represent the number of females participating in high school sports since 1971. So what we have to figure out, because here's our standard form, y equals c times 1 plus r raised to the t power. When we are writing an equation means we need C and R. We need this and we need that, okay? So I need to look for those two things. First of all, I see this number right here. This is my starting amount. Your starting amount is that 294,000. Okay, so in other words, that's your C. Then I see this right here. This is my growth rate. Okay, and I got to make it a decimal. So R is going to be, move it back 2 places because there's a percent sign there. So it's going to be 0.085. So you've got this for your C, that for your R, and here's your equation. Y equals 294,105 times 1 plus 0.085 raised to the t power. That's all that's asked in part A. Just write the equation. So there's my equation. Now we're going to use that equation in part B. It says, according to the equation that you just wrote, how many females participated in sports in 2005? Okay, so now in this equation, we need T. So the way we get T is we need to look at how much time has passed from the start time to the end time we're looking at. How much time has passed? So that's what I need to ask myself. How much time has passed from start to end? And the way we get that is by subtracting 2005 minus 1971. So 2005 minus 1971 gives me 34. Okay, so that means T is equal to 34. So if T is equal to 34, here's what my equation looks like. Y equals 294,105 times 1 plus 0.085 raised to the 34th power. And now I can type this whole thing into my calculator and get my Y value. So when I type that whole thing into my calculator, 294,105 times 1 plus 0.085 raised to the 34th power, I get y equals 4711004.36. Now, these are people, okay? These are females in high school sports. So the fact that these are people means that I cannot have a partial person. So I need to round. This 0.3 would tell my 4 to stay the same. So that's 4711004. That's 4,711,004 female athletes. All right. Okay, let's try the next one. Oh, this is the same question. We can skip it. Okay, let's try this one. In number 7, it says in 2010, the city of Farmington had a population of 21,087 and a growth rate of 1.9% per year. So again, the first step is let's just write an equation. Write the equation to represent the population of Farmington since 2010. So we need our C value and we need our R value. Those are the two things. So I see that we started with 21,087. So that's my C value. And then I see that my growth rate is 1.9%. So that means R is equal to, since I have a percent sign, I got to move it back 2 places, 0.019. So my equation looks like y equals 21,087 times 1 plus 0.019 raised to the t power. Okay, so that's part A. All I have to do in part A is write the equation. Now, apply your equation in part B. It says, what would have been the approximate population of Farmington in 2013 and also in 2017? So they're asking you to do this 2 different times. Okay, so again, we need to figure out how much time has passed. So if we're looking at 2013 and their equation started in 2010, 2013 minus 2010 is 3 years. So that's what I'm going to plug in the first time. I have y equals 21,087 times 1 plus 0.019 raised to the 3rd power. Go ahead and type all that into your calculator. 1 plus 0.019 raised to the 3rd, and I end up with 22,311.94. Now again, these are people. You can't have a partial person. So we're going to use that 9 to round it up, and we'll call that 22,312 people. Okay. Then it also asked us, what is the population increase in 2017? So in 2017, how many years have passed? So I need to take the 2017 and subtract the 2010, and I end up with 7 years that have passed. So now I'm going to take 7 and plug it into my t in my equation. Y is equal to 21,087 times 1 plus 0.019 raised to the 7th power. Plug all that in. Raised to the 7th, and I get 24,056.59. Once again, we're looking at people. So the 5, I'm going to round to the nearest whole person because you can't leave a partial person. So that 5 is going to tell my 6 to go up. I'm looking at 24,057 people. All right, so we're going to move on to our last example for our notes today. All right, so in number 8, it says the DNR has been tracking the deer population since, sorry, that's spelled wrong, 1970, and there's a rogue extra 1 there, sorry. At what time did, at that time, the deer population was 500 and has been increasing at a rate of 5% per year. Write an exponential equation, so that means we need C and we need R, to represent the deer population since 1970. So the starting number that I have is 500. I want to take a second to remind you or to point out, don't get confused between the starting number of something and the starting year. When you are looking for the starting amount, you're not looking for the time, you're looking for the amount that existed. So this is my C, and then has been increasing at a rate of 5% per year. So this is my R, and I have a percent sign, which means I need to take my decimal at the end and move it back 2 places. So that's 0.05. So if I write my equation, it looks like y equals 500 times 1 plus 0.05 raised to the t power. Okay, so there's my equation. Now I'm going to go ahead and figure out the expected deer population in 2017. So now the question becomes, how much time has passed? So that's what I'm looking for. So I need to take 2017 minus my starting year of 1970. So 2017 minus 1970, and I get 47 years. So 47 years have passed since we first looked at this. Now I'm going to fill that into my value. So I've got y equals 500 times 1 plus 0.05 raised to the 47th power. And type all that into your calculator. 500 times 1 plus 0.05 raised to the 47th power. And I end up with a number of 4,952.98, and it keeps going. And these are deer. We're looking at deer here, so we are not going to have a partial deer. We need to take that 9 and use it to round up the 2. So that's 4,953 deer. Okay, that takes us to the end of our video for today. Thanks for tuning in, and I will catch you next time.